Yeah, I think this will be a very different talk from what you commonly hear in recent years, because the deep learning, it's very dominating nowadays. And I try to develop a new learning paradigm and called green learning. So I try to give the definition and then talk about the techniques we have been developing for the green learning. So first, it's about some concern I have, and I think also quite a few of my friends have about the deep learning. I think number one is deep learning may be good for the companies, but it may not be very suitable for universities. And there are several reasons. So one is it demands a lot of resource, computing resource, and also data collection, labeling. These are not a typical university professor or student job to do that. And in terms of the GPU, university has much fewer GPU compared to companies. Company can run one set of experiments overnight, but we may need around several weeks. So this really not in university research favor. And another thing is it's really a problem-solving tools. So a lot of deep learning, you need to search the architecture, and then you need to adjust the cost function. And there are a lot of fine-tuning you need to do. And it's a black box tool, and also it discourages original thinking. In company, they solve the problem, so maybe they don't care how you reach the solution. But if you doing research in university and going along this direction, it's really not in our advantage. Another thing I want to say also, actually for industrial solution, learning still has a problem. And I will point out that later. But one is really about the model size. So actually today, on-chip memory, it's about 256K on-chip memory. So the model size typically is in million order. Okay, so if you want to do the deep learning, even in the client end, it's very hard to do just in single chip, and you need some memory chip and so on. So it's also an expensive solution. And so I feel there are a lot of practical concern in deploying the deep learning solution, even in the testing side. I'm not talking about even training. And this reminds me two fields. Okay. One is computer graphics and CGraph. So computer graphics was very, very popular, was very dominating in like a year 2000 and up to 2010. And CGraph was perceived as one of the most prestigious conference. But these days, we see the CGraph sort of the attendance and so on going down. And many academic people not attending CGraph anymore because they feel CGraph focus too much on the beauty of the content. So again, that because industrial people can put a lot of resources to generate very, very high quality animation, but academia people cannot do that. Okay, so I think once the academic people start to leave CGraph, then the attraction of the conference becomes smaller and smaller because there's really not a lot of innovation. Okay, then another thing is about the image video coding and then standardization effort. I will say these days a lot of new standards come out, but because all fine tuning, I think H.264 AVC is a very beautiful standard. I like it, but then afterward HEVC, VVC, it's all the fine tuning. So you can see the major players are companies, and it's very hard to find students want to do the coding in United States because they feel we just cannot compete with the companies. So, but a healthy society needs from both community, industrial interest and also academic interest. If you lose one of the party, actually the field is very hard to get a healthy growth. So now let's talk about green learning. And green learning actually is, of course, green machine learning. And in this approach, basically we try modularize the component. And this come back to the all day pattern recognition framework. So there is a feature extraction module and there is a decision module. The decision can be classification or can be regression. And feature extraction typically is unsupervised in the all day. Okay, so we do not use the data to do the feature extraction. But of course, in the past, it's handcrafted. And I think today we should avoid handcrafted feature extraction. But here, in the last 6 or 7 years, I developed framework. It's an unsupervised feature extraction. It's based on the statistics of the signals, like images, pixels, and like signal processing. And then the decision, we can use more traditional machine learning tools like the supporting vector machine or the linear regressor, logistic regressor, or the XGBoost, and so on. So this is a current green learning framework I sort of in my build up. And I think that there is a lot of new things we can do. So we keep developing the tools for the green learning. And how to define green learning? I think green learning should not be defined by just tools. Okay, so there are tools, but green learning should be defined by the characteristic of the solution. So basically, the characteristic we target at low power consumption. So in training and testing has to be low power consumption. It has to be small model size. So it's better less than 1 million parameters, so that there's a hope you can put the system on chip. And it's suitable for edge and mobile devices. And also, I think all this, particularly in low power consumption, we try to benefit the carbon footprint, right? To reduce the carbon footprint. And not only in the device, but also in the cloud computing. So I will try to go over the why we need green learning and some fundamentals of green learning, some technology. And then I will give a couple of good examples or say successful examples. And I think we are trying to do more and more. And I hope more researchers pay attention to this emerging field and willing to join the new direction. So first, green learning. So here, first I show this table. This is the convolutional neural network. And it's famous ResNet and different layers from 18 to 152. And this is the number of parameters from 11 million to 58 million. And I said, today, system on chip memory is a 250,000. So even we expect maybe we can have more memory on the chip, but it's very hard within a short time to go beyond 1 million. So this kind of things all need additional memory chips to go with the main CPU and the SoC. Okay, now this seems right, but no, actually there are something even more bigger, bigger. So this is for the natural language processing. So there's language models, and people are building more complicated natural language understanding machines. So the starting point is in a billion parameter. So like this is 2.5 billion, this 17.5 billion, and these are Turing natural language machines. And even more, okay, so why the natural language processing machine is so big? Because they use a transformer architectures. And this transformer architecture is more expensive than the convolutional neural net. Convolutional neural net, they share filters. So each convolution layers, there are a couple of filters, convolution filter, and they go through the whole part of the, say, the images or something. So each is a small block, the filter operating on a small block. But transformer basically is it's a whole image as a parameter, and then you go to the next layer. So it's it's a fully connected layer. So it's more like the fully connected layers MLP. So the weights, it's the parameter for the filter weight. It's very large, okay, and it's a multiply of input dimension, output dimension, all the possible combinations. So a transformer actually is very, very expensive. And now the example we show is a Turing natural language machine, but now there is another called the GPT-3. It's 10 times of the Turing natural language machine, and it's 180 billion. This kind of model, it's huge and it's data hungry. So it requires more of the label data, and then you can achieve the performance improvement. But sometimes people also has a paper talking about this kind of improvement really, it's worthwhile all the computational price you put in. So now let's talk about the carbon footprint of the deep learning. So let's just use the human life. Average 1 year human carbon footprint is 11,000 pounds. Okay, so that's 11,000 pounds. If you train a transformer, which is not very big, okay, it's only 200 million parameters. It's like a person live for 60 years. But that just try to train this transformer with the neural architecture search. It's already so heavy. And now you're looking at the billion of parameters. And with the neural net architecture search, it's really consumed too much power, and the carbon footprint is tremendous. So this kind of problem already been paid attention. But I think still a lot of researchers just ignore that and keep doing larger machine, and think just want to get a small performance improvement. It seems just that's the whole game about. But I think that this kind of value system need to change. So the green learning attempt to achieve is a low power consumption, and of course we want small model size. We still want high performance. Okay, may not be as high as the deep learning, but at least we have to close the gap as much as possible. And we want weak supervision. We don't want actually more traditional computer vision before 2012, before deep learning. Actually, a lot of computer vision problems, they are all belong to weak supervision problem. After 2012, things have been changed to be heavily supervised. And most traditional computer vision algorithm cannot scale with the heavy supervision setting. So they cannot benefit much from the heavy supervision. So, and deep learning can exploit that. When you have heavy supervision, like ImageNet 1.4 images, they can benefit from the heavy supervision. So the last 10 years, the research direction totally changed, and everything talk about the data, label data, heavy supervision. But I think it's a real computer vision problem. I believe it's still weak supervision problem. We really cannot build the supervision, this kind of label data, just infinitely, just to grow bigger and bigger. So I think that this weak supervision is very, very important. And also another is interoperability. This interoperability, many people have many definitions. What do you mean by interoperability? I think basically I try to say is we understand what's going on with the pipeline. Okay, so I will more examples when I go to the slide. So the green learning, basically I look the traditional pattern recognition. It's 2 modules, right? From data to features, so the feature extraction, and from feature to decision classifier or regressor. These 2 modules. But deep learning is 1 integrated modules. It's just direct from data to decision. So there is no sort of the partition line between the 1 and 2 modules. But I think that there are some advantage of modular design. Okay, actually, many engineering systems adopt the modular design. So, for example, you want to have a laptop. There are many modules inside. So, if you have multiple modules, you can debug each module separately, and then you can do the assemble the modules nicely. And of course, you can say, well, deep learning agent people also use the modular design now because say you have pre-trained a network, you have pre-trained convolution layers, and then you can use that to get a feature, and then you put other things. But if you consider pre-trained the part modules, this module actually used to be very large, because you want to fit more data and different kind of data. So usually tend to be a waste. So we are looking for a modular design and do a multitasking, can do more things, and then it's unsupervised feature learning. Okay, without any label, we should be able to derive the input data. So this, I showed a very simple example. This is a Lacan network 5-layer. So there's a 1 convolution layer, another 1, 2 convolution layer, 2 FC layer, and 1 output layers. And usually you put the image here, and you put the label here, and then do the backward propagation. And then once you converge, this part, this responses, we call this features, and this called the decisions. And so this feature is a byproduct of the end-to-end optimization. It's actually how you go from here to here becomes obscure. And different initialization, you have different filters, and the feature can be different. So this is called the repeatability. Deep learning, a lot of things, it's really your design and my design, even all the parameters the same, all the architecture the same. My feature and your feature can be different, okay, because the initialization can be different and so on. So it's another like a repeatable. What I'm looking for is given a set of images, and I want the feature to be identical. As long as I have some statistics of the input that say, the image set, I should be able to get the same features here. And I can fit into some decision modules. So then you really cannot base on the backward propagation. You need to figure out a way from here, go to here. Okay, so that's unsupervised feature learning. And also we don't want any handcraft approach. We need a systematic approach. And basically this can be done through the filter bank in the signal processing context. And I call this a subspace learning. So I can do the PCA and find the multiple filters and then find the response and pooling and so on. So this is doable. So this is basically what I want to say today. Okay, so unsupervised feature learning, basically we use the filter bank. So this filter is basically one filter, but there are multiple filters here. They operate on the same regions. So these multiple filters, they form a filter bank. Okay, and then we can get a joint spatial spectral representation. So there's a center, and we operate on that and come here. So there's a spatial information. And then there are multiple filters across this point. So there's a spectral information. So this basically you get a 3-dimensional tensor, we call it a cuboid. And this cuboid is a joint spatial and spectral representation. And this actually, this idea, we can go a little bit more later, but these kernels form a basis of linear subspace. So suppose you have 3 by 3 spatial location, we call spatial neighborhood. And the dimension is 9. If you have the region 3 by 3, the degree of freedom is 9. So you are able to find a linear space. It's a 9-dimensional representation. So it means you can get a 9 filters and get a 9 filter response to get the equivalent representation of this 3 by 3 spatial point. So we call this just a change of the representation. And then we can do the subspace approximation. Means there are some space, some filter has a very small energy. There are some filter has a larger energy. Then you are able to throw away some channels with small energy. So this is related to like a compression. We can do the discrete cosine transform. We can view this discrete cosine transform. We have a 64 filter, it's A by A. And then we can throw away some high frequency and keep some low frequency. So that's another way we can look at the filter bank. So one filter bank is a famous one. It's called a low 3x3 filter. So the spatial domain is 9 pixels, and you can have 9 filters. So they span the same space. So you can use the frequency representation, use the filter representation to represent the space, or you can use the 9 impulse to represent the space. Okay, and this is often used for the textual analysis. So let me use this to explain the idea. So if you have image n by n, and suppose you have the 3D tensor, and then you can consider the filter size is 3x3. So then after you apply this 3x3 filter, and without any padding, you are able to get output n-2, n- times 9, because there are 9 filters. So that's the output. So it's a 3D tensors. So the response of each filter indicates a frequency component of local neighborhood. But the loss filter has one shortcoming. Is the filter coefficients are fixed. They are not adapted to image content. So you can see all this filter coefficient just fixed. So if you want to do data-driven, you really want to adapt to the statistic of the underlying input data, the input image. And also it's only one stage. Okay, and then you are only able to get the representation of local patch, local block. You are not able to get a mid and long range neighborhood. So in order to generalize that, of course, we motivate by the convolution layers. And so we define a sub-transform is a subspace approximation with adjusted bias. And this is the loss filter bank. It's a variant of the PCA. So it means basically we can, for 3x3 spatial location, first we can compute the local mean. We usually call the DC component. The current component means it's a DC. DC is in the circuit term. It's just local average. And then we can use the pixel subtract the local average and get the other residual signal. And then we can apply the PCA to this residual signal. And that's called the sub-transform, okay? And also we will talk about, we can do not only one stage, we can do multi-stage. Just like a multi-layer convolution, we can do multi-stage sub-transform to achieve the similar effect. But remember here, we do feed-forward processing, go from the image gradually one by one. There's no backward propagation, there's no optimization. You purely PCA, find the mean, and then do the PCA on the residue image, AC component. So basic sub-transform is a subset into one DC subspace, which is 1111 is a local average. So this is one space, and the rest is orthogonal to that. That's an AC subspace. And then we conduct the principal component analysis on this AC. So the residue is still 3x3, but if you do the PCA, you will find there's one channel energy is 0 because the degree of freedom is here. So basically you can have a non-zero energy AC channel. So one DC channels and 8 AC channel. AC means alternating current. Again, this term borrowed from the circuit theory. The circuit theory, we have a direct current and alternating current. And so here we use this term, DC and AC. So if we have a grayscale image, we can do 3x3 by 1. 1 is the channel, means the grayscale. But if you have the color, then this will be 3. Okay. So one DC filter, this is a constant element filter. AC filters. And this basically you can obtain this by doing the covariance matrix and then find the eigenvector. This eigenvector will give you the weight of the filters. And this output n2 n-2 by n by 9. And why not apply PCA to 3x3 patch directly? Because when we do PCA, we need to subtract ensemble mean. And ensemble mean actually is sensitive to the different image input. So we subtract the DC, actually the ensemble mean will be close to 0. So then we don't need to worry about the ensemble mean anymore. We just remove the DC, then the ensemble mean will close to 0 vector. Color, so we have 3 by 3, this spatial. This 3 is RGB, 3 color channel, and we do this 3 by 3 by 3 subtransform. So this then 3D tensor, 1 DC filter, 26 AC filters. So total the degree of freedom is 27. And in this common filter, in this spatial filter size, you can choose like 2 by 2, 3 by 3, 4 by 4, 5 by 5, and so on. Okay. And we should avoid the use of large filter size because the correlation between long-range pixel is weaker. Okay. And the way we do is we do the one-stage filter, and then the low-frequency part, we can do the downsampling and then go to the next layer. So then we are able to consider long-range pixels through the pooling operation. So also we have lossless and lossy subtransform. Lossless subtransform, basically we can, the input is n by n. Suppose the filter size is 2 by 2 and try equal to, means non-overlapping. We just do the non-overlapping subtransform. We are able to get a lossless transform. And most convolution operation is with try equal 1. Then try equal 1, actually there is some overlapping and there are some redundancy, but we can remove the redundancy by the pooling. Okay. And also another lossy subtransform is we can discard channels with very small energies, and that's the equivalent to dimension reduction. Okay, and so this is the one stage, and this is the go from, say, there is a center pixel, and there is a surrounding neighborhood, and also there's a spectral components. So there's a 3D tensor, and then we order them to a vector, and then we can do the DC and AC decomposition, and then do the P on the AC, so dimension reduction. And now the center, the dimension has been reduced from this one to this one. Okay, so basically we find a neighborhood, define a neighborhood, and then we do the subtransform. So then that will be the next stage input. And then next stage, we do the same thing again. We do collect the neighborhood, do this and so on. So we can go from the very fine spatial resolution to closer spatial resolution. So this we define a subtransform. So the input will be spatial is this SI minus 1, SI minus 1, and KI minus 1 spectral 3D tensor. And then we can do the one stage, get another 3D tensor. So SI minus 1, and KI. So that's one. And we look at the correlation structure. Actually, these are the 3 data sets. The spatial correlation actually is stronger. So particularly some low frequency channel, there is strong spatial correlation. But in the spectral component, the correlation actually is weaker. Okay, and this one actually we can exploit this property to do the more computationally efficient transform. It's called the channel-wide subtransform. So if you do the straightforward subtransform, this is a more follow like convolution operation. It's the input like that and output like that, and then there is some small filters. But actually, we can decouple this one DC and multiple AC. And this multiple AC, actually, they are uncorrelated. And so actually, you are able to just look at one channel at a time, using the spatial neighborhood to do the subtransform. So channel-wise, so this blue channel, orange channel, yellow channel, each channel you do the channel-wide subtransform. And so this will simplify this 3D tensor operation to just 2D tensor operation. So that can also save you a lot of computation. So this just shows the example of the 3 hop. Suppose you have 32 by 32 by K, and then we can do this is the like low frequency channel. this high frequency channel, and this high frequency channel, the correlation between the spatial domain is very weak. Then there's no need to go further. We can stay here. And this one, and we do the pooling, and there's still strong spatial correlation. Then we can do another subtransform, channel-wise, only spatial channel, decouple them. And then there's do the pooling again. And then this is the low frequency and do the pooling again. So eventually we have all the leaf node. And then we can use this leaf node as a features. So there are questions about the first, whether the subtransform linear. The answer is yes, but actually it's a affine transform because we have a constant term. So it's a affine transform. But now the people will say, can a linear transform yield powerful features? I will say nonlinear classifiers are very important, but linear feature may not be that bad. It's very easy to understand. It's a representation. So you are input, actually you are doing compression. You are finding a compressed representation. So the feature is explained. And you want to do the classification, one way you can do is the clustering. So the clustering can increase the power of the sub features. So you do clustering of the feature and then do the decision. Okay, so here I want to show the multi-stage processing. This is unsupervised feature learning. We don't need any label. We don't need any backward propagation. We just doing this sub transform. We call this a pixel hop. Pixel hop, hop means neighbor. So pixel and its neighbor form a linear space, and we transform to the spectral domain. Okay. And then we do the pooling, look at some low frequency channel, there's correlation. We want to go to the next layer and then do pooling. And then we find the neighborhood, do another transform and do pooling and blah, blah, until very low spatial dimension, but very long range correlation. So this is feature extraction. We don't need to worry about. So it depends on the input images. The statistic, the PCA will look at the local features. So there's a local PCA, this middle range PCA, this and then we can somehow combine the features. We do certain aggregation, and then we try to do the label assisted regression, and then get a dimension, and then we can do decision. I think that this part we modify it. This is like the 2017-18 work. Now these days we have some modification on this. Particularly we use more XGBoost. So I will not emphasize this too much. So I think that the focus I want to show is this feature extraction pipeline. It's unsupervised. And later on we can do many different classifiers. Okay, now I want to explain, want to show some examples. So one is test the water, right? Using this unsupervised feature to see whether we are able to achieve reasonable performance. So this MNIST data set, facial MNIST data set, it's all small images, or the dimension 30 by 30. This color is a grayscale, and we look at the top one classification accuracy. And LANET5, this is like a benchmark, and this feed-forward is our development. We basically use the LANET5 as architectures. We designed the filter using the feed-forward path, and it's not that good, so there's some degradation. But then we use the pixel hub we just described, and this pixel hub plus is some kind of a little bit and we are able to outperform the LANET5 in all cases. Okay, so means actually it's okay. We can use the green learning to reach comparable performance of deep learning. And in terms of training time, and I think this is so if you do the LANET5 MNIST, facial MNIST takes so much time. This is the CPU. Okay, we use a CPU. We don't use a GPU can do much faster, but we want to compare the CPU, and we are able to train these parameters or derived from it faster than LaNet5. One thing I want to supervision. So this is a number of label data. So if you have the number of label data more and it go down, and similarly everything go down. This is the LaNet5, the green. So it's the accuracy drops faster than the purple line, which is pixel hop. So it means if you have smaller training data, actually of this pixel hop. Okay, and similarly for the facial amnist and also for CFA10. When the training data is less, able to be more robust, the degradation is slower. And then we derive the P plus. The difference between the pixel hop and pixel hop plus is the basis. One is the full subtransform. One is use the channel-wide subtransform. The channel-wide subtransform I described, it do transform. Then all the channel 3D tensor to do the transform. Complexity is lower, it's faster, and let's see the performance. Actually, the performance it's a little bit worse, but the complexity actually it's lower. This is the model size. If you compare the LaNet5 model size and look at the pixel hop model size, actually the model size is much smaller, even with the LaNet5, which is considered very small, 61K. We need like a 30K and so on. Okay, so then let me talk about the application. It's a fake image detection, and we have the paper presented at ICME last year. So this is a deepfake video, and this original and this fake. And usually it's very hard for people just given one. Okay, given one is very hard. Even two. You're still hard to say which one really which. Okay, so this is a challenging problem, and the most state-of-art deepfake hop deepfake detection is based on deep learning. Okay, so either you do the CNN, try to find, and sometimes you also use the RNN because it's a video. So you have time series. So they're basically doing this kind of architectures. But again, the size is large, containing very large model parameters, training very expensive, and they are also non-deep learning based. Performance not good. So lightweight and non-deep learning based and basic green solution. So our approach, basically, we have some pre-processing. We try to find the landmark of the face, including these are the standard tools we can borrow to find the landmark, so that we can find the left eye, right eye, the nose, and the mouth. So these are the several regions we select. And then for each region, we scale it to the 32 by 32 and the 3-channel RGB 3, and then we can do the pixel hop plus, and and do the pooling and the second hop, third hop. So the resolution becomes smaller and smaller, means more global, and this more local, and then we do PC and so on. So all this feature extraction all feed-forward, no backward propagation, just one pass feed-forward, and then we do the PCA and do channel-wise, and then do the ensemble, blah, blah, blah. So this is sort of just quite a standards and so on. And I want to emphasize, we use the same methodology, apply them to the region of the human face. And this I explained before, we can do the channel-wide sub-transform. So this is the model size of our system. So the system, the model size is around 43K. So it's definitely fitting the chip on. And here we consider the two data sets from the first generation Deepfake, and so this is the first generation, and then also two from the, and so these are the parameters of the data set. There's a real, how many frequency, how many fake, how many training, how many testing, and so on. So here I'll give you a big table of the performance comparison. So I want to show you our solution. We call a solution called Deepfake Hub. The first generation, we are able to achieve this data. We are able to achieve 100%, and it's give the same as the exception net. For the second one, we close to the best. So this is the best, this is second best, and we still close. And for the second generation, this is considered a harder problem, and most are not doing well. And this one is exception net 83.6, but we are able to achieve 95%. And then this video based, this is frame based. So look at second generation, our performance really outperform a lot of solutions. And deep learning solutions, you can see most of the model size in the medium parameters. And only this guy is 1,000 parameters, 27. But this basically is a shallow, very shallow network. And the performance-wise, it's very poor. So it's very, very poor. So the other are all very deep networks. Okay. So here show another very successful example. We are able to achieve good performance, actually outperform the deep learning solutions, and with a much smaller model size. And this shows the area under the curve value for each facial regions, and left eye, right eye, mouse samples. And then we show some kind of a different kind of solutions and so on. And so this again compare different kind of ROC curve of the different solutions, and this is our solution. We can get like 100% AUC, and the other, we can get a good result. And this one shows the training samples. So actually, this is left eye, right eye, mouse, and ensembles result. Ensemble is the best, but we are able to, we can achieve 85%, say here, 85% AUC, area under curve, but with less than 5% of the whole training. So basically, our performance degradation, it's much, it's really slow when you have a smaller number of training videos. And these are the, we can show the result, and this is a fake, 89% fake. And this is like a true, 94% true. So this is a celebrity second generation data set. Right now, there's a third generation data set. We are working on it. So the Facebook came out the third generation data set, and we are working on it. And now we are reaching very similar performance as the best solution, but again with a very small model size. Okay, so this is the real. And this is a fake. Okay, so you can find our code in GitHub, and you can feel free to try it. So here, in the summarize, the presentation basis small model size, fast training, high detection AUC, and needs fewer training samples. Okay, so the last part, I will talk about the point cloud classification registration. So we published a sequence of papers on this topic. So point cloud processing is very popular this last several days. The publication number grows very, very rapidly. And point cloud, of course, it's important because it uses autonomous driving, and you have the LiDAR data to look at the environment and measure the depths using the time of flight concept. And we consider net 40 and ShapeNet model, but actually we also have extension work to look at the large indoor point cloud, and also we are looking at outdoor point cloud, but I'm not going to say here. I just try to show the essential idea. So I use the green learning to do the two jobs. One is classification, the registration. So again, what we try to do is for deep learning, you point cloud input, and you have the label data. For example, what is this table, right? And you give the table, and you design the network, and so that you are able to do the backward propagation parameters, and then do the decision. So in our system, we want to do unsupervised feature extraction. And so it's a white box. The feature can be explained, and then later on, once we feature, and then we put the classifier. Okay, and so the foundation is still subspace, successive subspace learning, actually faster training, and also we can run on CPU. So now this is the point. You have the XYZ 3 coordinates. So you basically n times 3. N is the endpoints. Each point has a XYZ. And then that's the input. And then we can do the point hop using the point, find its neighborhood, and do the local transform. And then do the pooling. And then you repeat the same process. And then you aggregate and then do the classification. So the neighborhood, we can use the KN, the K nearest neighbor, to define neighborhood. Then we partition in the A octant. Okay, for these points, the center is the red dot. Every point can be the center. And then we find the nearest neighbor and look at the A octant. And then we look the nearest two, or within the radius, we find the nearest neighbors, and then we do the local average. So local average, you get each octant, we do a one mean. So you basically have XYZ mean in the first, second, and so on. So basically the XYZ for each octant. So you have 8 of them, so it's 24 features, the feature for the neighborhood of this red dot. And then every red dot, every point we can do the same thing. And then we can do the dimension reduction using the subtransform. So basically this is your input, we do this transform, and then there's an endpoint. Each point now has the D. So 24, we may be able to reduce to say 15, and then N. And now 15 channels, DC, we need to go to the next one, and we can also look at several AC. These AC are separated, they are decoupled, and we can each AC we can do the same thing. So we can we don't need to go to the next layer, next hop, and some we can go to the next hop, and so on. So and we can each channel is just a neighbor, and we keep doing this channel wide 3D. Point subspace and so on. So I want to show you the supervised feature learning and unsupervised feature learning, and compare our methods with the supervised deep learning methods. So our method, point hop or point hop plus plus, the class average or the instant average, actually performance is close to the point net. Point net is considered like early good neural network for the point cloud processing. So we are close to that. And so, okay, there are better point cloud classifier these days, but I think our performance gap is not that big. But also, I feel there are ways to improve our solution as well. So I think that this work all several years ago. So we have a new idea how to improve it. So this I want to show the time and the model size. So the training time, the PointNet plus and DGCN is a GPU this hour, 7 hours, 21 hours. And the Point Hub and Point Hub Plus use the CPU, and the time is a minute. It's less than 1 hour, less than 0.5 hours, so like 20 minutes, and so on. And the inference time is also okay, but the GPU will be faster. So this comparison may not be fair. And the model size, we only have 159K, and this model size is 1 million, and so on. Okay, another thing is about the point cloud registration. And so we have 2 point, and there is a different kind of shift and orientation, different kind of rotation, and we would like to align them together. Okay, so this is a registration algorithm. And there is a standard procedures. If you are able to find the correspondence, then you are able to use the there's a target point cloud, there's a source point cloud. Once you know the correspondence, you are able to solve this rotation matrix, translation matrix, minus the point-wise mean square error. Okay, so this is the basically this is the parameter we are looking. We are looking the translation vector and okay theta x, theta y, theta z. So this is our point hub registration point hub. So basically this is like it's a modified point hub. I want to talk a little bit about this. It's using the local reference frame rather than global, and then we can do 1 hop, 2 hop, 3 hop, and then we can find a feature space, and we can align the point in the feature space. So if the points are similar, means they have a similar neighborhood. For example, the wing of the airplane at the end, the wing end is very spatial, right? The airplane, the head is very spatial. If you look at the chair, the stool, the bottom is very spatial. So this kind of very spatial point, it can be described by neighborhood, and this neighborhood can be captured by this point hub features. And so we want to compare feature similarity, and then we are able to also look at the spatial correspondence, and then we build the correspondence, and then we are able to solve the single translation using the singular value decomposition. So here, it's an important thing is to look at the local reference frame. So we cannot use the earlier point hub, because earlier point hub, you want to do classification, chair aligned, table aligned. But now the chair being rotated, so the octant will be different. So we need to find the local reference frame so that to sort of standardize that. So there's a point, and we want to find the local reference frame. We can use its neighborhood and to find a principal component neighborhood, and then using this principal component, the major axis, the first component P, second component Q and R. So every point you use its neighborhood to find a local PCA first. And so you can have a local reference frame. And then once you find the local frame, you fix it. And then using this local frame to find the point hub features. Okay, so for each point, we first find the k-nearest neighbor, and then using the PCA to find the local reference frame, and then we can find the PQR coordinates. But the PQR here, we need to pay attention to one thing is the covariance matrix, by each eigenvector has two directions. Point, positive and negative, both are eigenvectors. So we have to find unique ways to select one eigenvector. So it means if the PQR, you have the two different direction, so R plus R minus R, people choose different direction, then you are not able to compare the features. So in order to compare a feature, you need to find the sign. You have to choose those two directions and choose one of them. And this direction actually is not that difficult. So basically, we have to find the neighborhood, and then we can using some kind of a moment, and then if left moment the right greater than right moment, we flip the sign. So basically, we require the right moment has to be greater than left moment. So we use the moment to choose the vector directions. And then we can use the multi-hop to get more global features. And so I think that this is basically summarize the feature extraction using local frame, make feature inversion and translation, because we use a local reference frame. So the rotation and translation will not change that. And the high range point relationship, no class label needed. We just need a point cloud scan, and then we don't need to know what's the ground truth to learn the kernels, right? The kernel has nothing to do with typically people do is a random rotation and random translation. So people, in order to train the registration, means you give them point cloud and you rotate a certain angle, and keep doing that and using that as a label. And so it's a self-supervised. You rotate a point cloud, a certain angle, shift a certain location, certain displacement, and using that to train a network. But we don't need that. We just need one point cloud. We don't need a lot of different pairs to train the filters. And one pass feed forward, and this part independent of the rest correspondence transformation modules. And in order to build the correspondence, first we have to consider they are close in the feature space. So these are the target, and these are the source and target, and look at the closest point. And also we build something that means the feature, sometimes the closest one and second one are very close. So it means this feature actually has many close feature points. So this is not very good. You want to have someone, it's only the closest one, it's only one. The second one is far away. So that's a good choice. Okay. So it means there's only one point look like you, but the second one is far away, then it's a good choice. Okay, and so once we build the correspondence, and then we are able to solve the SVD. Okay, yeah. So these are some different examples. We can build the correspondence. These are it show the correspondence, and the correspondence actually is very consistent. And once we have correspondence, we can use a singular value decomposition to find the rotation matrix and this translation displacement vector. And so we do the ModelNet 40, and there are 40 classes, and we do the alignment of the two, and we do the arbitrary rotation and arbitrary translation, and then test the alignment effect. So for the training, we use the target point cloud, and for the testing, apply the random. So this is our training. We just use the target. That's it. We don't need to worry about the source. And for testing, we apply the random rotation and translation along 3 coordinates to get the source. And rotation, we uniformly sample between 0 to 45, the translation, and then compare with different methods, and then look at the mean square error, or root mean square error, or mean of absolute error. The smaller, the better. So here we can show, actually, this is our solution. And this is the relate to the rotation matrix. And this is the translation vector. And the mean square error, you can see ours actually is the smallest. Okay, and the translation, the same thing. And this is a unseen class. So this unseen point cloud means we maybe see some point cloud in the same class, but we apply to the unseen instance. There's an unseen instance, but you see the instance in the same class. But this is unseen class, means I don't even see the car at all. I never see the car, and I can get the performance. And this is actually tougher than this. Okay, and here our performance base the same. It doesn't matter whether you see or you don't see, you still can see, you get about the same result. But deep learning solution actually, for example, you use DCP. If you know the class, but you don't know the instance, it's good. But if you have you don't see the class before, you never see car, and you want to do the car, then the error becomes more significant. So we have submitted a paper, and reviewer puzzled. They say, well, they don't know why this happened. Okay, and then the explanation actually is easy. Is you do the backward propagation, your label influence the features. Your feature affected by label. So you basically overfit a small number of classes. So suppose you have the, say this is called a flower pot. You never see this before, but you see car. Okay, so once you see car, your feature actually overfit with car class. But when this class never show up, and you want to fit this one, you cannot do a good job because your feature been polluted by the other classes. But in our case, we really don't care because we never use this information. So that's a very interesting insight. Backward propagation may not always happen. Sometimes it hurt you. If you by some classes and you never see that class may get a penalty. And similarly, we can also look at more real thing. We add perturbation, we add some noise, and then we can add ICP to overcome the noise effect. And we can get a very, very small registration error. And also we apply to partial data. So the airplane, this cut is a cutoff. We are able to do a very, very good registration performance. And this is a real world data, the Bunny, and so on. So again, our performance just much better. Okay. And these are different kind of real world. So, and another very interesting is the performance usually when people do training, maximum rotation angle is bigger. You have random selection, but allow maximum rotation angles. The rotation angle bigger, the performance become worse, and so on. But our solution, actually, it's independent. We really don't worry about the maximum rotation. We still get the error is flat. So here I want to talk about the training time model side resource. So point the net LK or deep close point. This base is the best in the deep learning. The training time is 27 hours using GPU. The model size 21 million parameters, and resource you need 8 GPUs. Here we only need 40 minutes using CPU plus multi-threading, and model size 200 200 kilobyte means the 200,000 parameter, but we use byte. So it means this can be put in the system on chip. If the system on chip 256, this is okay. It is 2. You can see the big difference. And even here, which is such a low cost, but it's the performance. So it's time to give the conclusion. Of course, so far, not every examples we outperform deep learning. I select very good examples, but I'm confident gradually, we are able to expand the applicability of green learning to deep learning, the sort of the application domain. Some people ask me, Professor Guo, when are you going to get the ImageNet result? If you can do ImageNet, I believe you. Or say, Professor Guo, when can you do the YOLO type result, object detection? If you can do that, I believe you. It's doable. I feel, okay, I still feel it's doable, but it takes a little bit longer time because the complexity of problems. But I feel it's doable. So it may take 1 year, okay, I estimate, but we are working on it. We are working on the larger images. We are working on Pascal data set. It takes a little more time to do the object detection, object classification, but it's doable, but just takes some time. But again, right now I feel the green learning, the human resource is too little. Okay, we still have a very small number of people working on this. It's just emerging, and I will say most papers is from my lab right now. But I think I've been working on this for the last 6 or 7 years. And I feel I will continue to devote to this and for the next decade. And I hope I can see the prosperity of the green learning. And okay, so in terms of similarity, green learning is a successful, and deep learning is a gradually enlarged subfield. So this is has a similar flavor. And deep learning is optimization. Okay, so it's using a lot of backward propagation to do it. But here we just use the statistics, try to find the local statistic of the local neighborhood. And then I show you the image, I show you cloud, and so on. So we can do that. The information base is try to trade the spatial information to spectral. Spatial is very hard to know the pattern. So when you do the transform, you can start to see the pattern. So spectral information is important. Okay, so we do this kind of transform and sub. And deep learning also do the tensor, right? So you have the gradually spatial dimension reduced, spectral dimension become larger and larger. It's very hard to find the explanation, but in spirit, I believe they also try to find patterns. In spatial information reduction, we can use a spatial pooling, and deep learning also use spatial pooling. Actually, we borrow the idea from deep learning. But the internal differences, green learning is a metric model because it's just a transform. You can select a number of parameters you want. You can select the number of channel you want, and you can go to the next hop and so on. But it's a signal processing pipeline. Right? But deep learning is different. You need to decide architecture first, and that's a parametric model. And once you have the model, find the model parameters. So that's optimization kicking. Incremental learning, actually, the green learning is basically, I just need to see the new samples go to my pipeline, and I can extract new features. And once I find the features, then I can feed into the classifier. Deep learning, actually, there are a lot of papers published on the incremental learning, transfer learning, but fundamentally, it's a very difficult problem. Model architectures, the green learning actually very flexible. I think I emphasize the feature extraction. The classifier actually, today we all most do the XGBoost and simplify a lot of pipeline. So I don't recommend our early work. The decision is still too complicated. I think there are a better way to do it for the classification or the regression part. I think it's the network architectures. Interpretability. So basically, green learning base is find the representation. Okay, so it's a follow like compression philosophy. And then once you have the feature derived, and then you can fit in the more a lot of machine learning tools. And this end-to-end optimization is really hard to explain what's the meaning of particular layers. And model parameter is a feed-forward, and the deep learning, the backbone propagation. Testing complexity is a significantly lower than deep learning. And this is an explanation, is a subspace approximation. Deep learning is very hard to explain what the meaning of the filters. Basically, well, you do this, you get the best, lowest cost function. Okay. And task independent features, this is a multitask features because it's task agnostic. But deep learning, of course, it's there's a task in training the feature, and a lot of it is pre-trained network, and then you can use pre-trained network to other tasks. But no one knows whether that's the best feature, right? But usually the pre-trained network is very, very large, so that's already so expensive, very expensive. So sometimes your data is really very few, and you still just use the very large network to go through the small amount of data. Multitasking is easy, relatively easy compared to deep learning. And also you can incorporate priors and constraints. And because we are not doing the end-to-end optimization, we are doing the local optimization. Each module is local optimization, and we can add another modules. And weak supervision, actually I can show many examples. Our system is much more robust to the smaller data. So the green learning solution is not data hungry. And the adversary attack also is difficult because again, it's divided into different modules. So each module doing the things. So the attack can attack the classifier, but the attack cannot really attack the features. So if you do the small perturbation of the image, the feature extraction will kill all those small perturbations. Because the small perturbation, all high frequency, they will not show up in the final feature extracted. Okay, so I think that's concludes my talk. I'm open for questions. We still have 10 minutes left. Just welcome to ask me any questions.
Thank you, Jay, for a great talk. Yeah, very interesting insights. Excellent. So I think for the questions we can, people can put them into the chat. And if somebody would prefer to actually ask the question verbally, let me know. I think I need to enable people to speak. Don't know if I can do it generally. No, I think I have to do it one by one. Yeah, so please feel free to put your question into the chat as well. So maybe I can get started to just people can think for a second. So one question I had, actually, you kind of answered on the last slide. That was the one about incremental learning, which is really an interesting area. And you mentioned that your method actually makes it much easier to do incremental learning if you have additional classes that you want to add. So that's great. Another question that I have, is it easier to then have a parallel architecture or parallelize your framework, which is one of the issues in some of the other models, right? That it's you have to do certain things serially, sequentially, rather than being able to do it in parallel.
I think that the convolution operation, actually, the GPU can speed up because once we design the filter, the operation, I will say, it's really like the neural net convolution layers, but actually more efficient in the sense because channel-wise. So it means you don't do the 3D to 3D, XY and spectral. You are doing the 2D to the 3D. So it means you have XY for one channel, and then you do the sub-transform, then and channel, right? But each time we only look at one channel. So again, we just look at spatial dimension, do the transform, and get a spatial spectral. But once spatial spectral, we decompose to spectral again. So it's basically it's a 2D for the image. For image case, it's a 2D. But using the GPU definitely can speed up. We don't use GPU so much. Is my students are not very good in GPU optimization. So I think because the code just runs so fast in CPU, so you have to do it. If we want to port everything to GPU, it's possible, but just you need to really some people support the lower layer, programming, those GPU programming. So yeah, so it's a little bit, but in principle, everything can be implemented on GPU. But again, I think whether we should do GPU or CPU, it depends on industry need. I think we desperately need industrial collaboration. We need like Google willing to do TensorFlow. We need some company willing to do something with USC on this green learning and build the support software platform. Yeah, so we are lacking in that aspect.
Yes, and being able to implement these algorithms in like edge devices, etc. I think that should be a great benefit, right? That some of these classifiers can be moved to the edge into the low power devices. Hopefully there should be some industry interest in those areas.
Yeah, I think I got a question about the image classification, but the more complicated data and so on. Well, I think honestly speaking, it's a long tool. Okay, so in the beginning, everything just fuzzy and not clear to me. And actually, I couldn't even find any student willing to do the green learning. It's for them, they feel it's too risky. What's this? What Professor Ko wants? And he was not even clear what he wanted. So in the beginning, I have to even write a single author paper because no one wants to do. I need to find an undergraduate student to run the experiment. Okay, but now I convince all my PhD students. They all believe this is the right direction to go. So they are willing to spend their time, effort on this. So that's already a big, momentum. Okay, so I graduated like 2 generations of deep learning students. They all gone. They all left. So then all the remaining students, they are new generation, means they came to USC day one. I just tell them you have to do deep green learning, otherwise find someone else. Okay. So anyway, so I think the speed up right now, I feel we are really in a speed up stage. The thing become, in the beginning, always a slow start, exponential curve, always slow start. But now I think that the things become clear and clear to me. So I have so many different ideas how to improve the green learning. So the feature extraction is one thing. And also we need to figure out a way to do the multiple features. So because our feature is fixed and you have the decision. So if you have something close to the decision boundary and feature cannot be changed, then you are not able to partition the data well, sample well, right? But deep learning somehow can backward propagation, adjust the feature so that make the feature very nice so that to fit the decision. So that's the advantage of the end-to-end optimization. But the way we compensate this is we do the multiple features. We do one pipeline, one feature, but then we do another pipeline, another feature. And then we can, using the hard samples, means the borderline case in the first decision pipeline, fit into the second pipeline. And second pipeline feature has to be changed. Cannot keep the same. Means, for example, we use 3x3 filter. The second one, we use 5x5 filter. So we change the way to do the filter extraction. And then we may be able to partition the data on the borderline, the decision difficult case in the next pipeline will be better. So there are many ideas like this coming out these days. So instead of doing single pipeline, just one feature, we can do simple to hard. progressive learning. Okay, and it's still very simple, but just allow some difficult decision going to the next pipeline. And so there are many other things we can do. And also, actually, we are developing a new classifier. We are doing a total new thing about the classifier. We call the Subspace learning machine. And it has it's another supporting vector machine. It's another extreme learning machine. It's not XGBoost. It's really a new machine learning classifier regressor. But it will come out. So there are many things will come out like a package, many things will come out together. It's all green learning, okay? Because if you're not green, I'm not interested. I'm only interested green and explainable and elegant solutions. So we'll see, okay? You just pay attention to more publication from my lab. We push the green learning a lot, but of course, in some sense, this is deep learning is a big ocean, and we are just like a small leaf. A small leaf on the big ocean. So really, who cares about the leaf? It's a big ocean. So yeah, it will be hard, okay? But we try our best. Let me see. Sustainability was a major advancement compared to the traditional non-deep learning. It seems to me you propose green learning somewhere between. Yeah, I mean, this one actually is not very different not very similar to the traditional non-deep learning. Traditional is a lot of handcraft feature. I don't think it will work. Like SIF considered very powerful and this and that. I think those handcraft feature is really not extensible. When you have a lot of data, there are always corner cases. So you need some model a little bit larger. Okay, those traditional computer vision tool like SIF, the model is too small. The model too small to scalable, very large data. So the performance always there is upper bound. So the way I look is I can use the old model to do easy samples. So there are easy samples, 70, 80%. I can use the simple model to take care of things. And then the hard sample, I need to build a new pipeline to take care of the hard samples. So it's again, as I said, easy to hard progressive learning. But I think again, the feature extraction got to be automatic. And the automatic, we use the PCA and using the compression idea to do the feature extraction.
Okay, great. There are a few more other points.
Yeah, some people ask about the ImageNet.
ImageNet,
actually,
yes.
I think the current issue of ImageNet is the green learning actually learn well for small image, 32 by 32. And when the image become bigger, and the dimension become huge, you will get like thousands of the feature dimension. And how to manage those manifold, how to use that, that's really a very challenging issue. In deep learning, they don't care. They just build a very large network and they take care of the thousands of, because they have millions of parameters to take care of the million of images is not a big deal, right? ImageNet 1.4 million images, but they have 20 million parameters. But I think we basically need to go back like an image pyramid. So we basically have to consider big object, but we can resize the images and get that 32 by 32. And then there are something we have zoom in, a small object, but we have zoom in. So it means we have to do a lot of divide and conquer and so on. It's just messy, I have to say. It's messy, but it's doable. So I feel, and the messy, only the first pioneer will be messy. But once the pioneer finishes the messy job, for other people will not be that messy. Okay, but it's really messy for us. I need a student very patient, really. You need a very patient and willing to do it step by step. And I'm working with them closely.
Okay, yes. I think for this kind of paradigm shift, there's always, there needs to be some pioneers who dig into the problem until it can be further established. Yeah.
Yeah, in terms of the adversarial attack, basically, we don't have bandwidth to work on that. But basically, I want to say is whatever people do at the adversarial attack is visually not obvious. Means turtle is still turtle, right? But you can decide. But the human sees turtle, so it means the low frequency part is correct. It really is some high frequency part for you. But in the green learning, we use the basic compression principle. We're using the different kind of PCA low frequency channel. So those high frequency will be filtered out quickly. So those high frequency perturbation, if you do the adversary, adding a lot of small, very high frequency, they will not show up. They will not show up after feature extraction. So turtle still turtle. The feature will not be changed because you add some small perturbations. So I think in terms of feature learning, it's much more robust to adversarial attack. It's based on this argument, but we haven't done the. I personally feel the deep learning is the end-to-end, and end-to-end you want to optimize the cost. That's good, but on the other hand, there are a lot of price you pay. So that's kind of small perturbation sensitivities and other issues, and also transfer learning, incremental learning. It's all very hard. Even a lot of people claim they are working on that, but just very hard to make it right. Because this is their weakness, okay? But in a lot of things in the green learning, actually, this becomes not that difficult because we know what's going on, we know how to handle it, and so on.